Welcome to the Empowering Tomorrow's Automotive Software Podcast, brought to you by ETAS, a single source of cutting-edge software and hardware solutions that make automotive embedded systems safe, smart, secure, and sustainable. Each episode, we'll be joined by ETAS and industry experts to discuss how electrification, automation, and connectivity are impacting the automotive industry. Now, sit back and enjoy the discussion.
Hello, everyone, and welcome to the Empowering Tomorrow's Automotive Software Podcast. I'm your host, Zane Pelletier with ETAS. I am a penetration tester and reverse engineer, and today I'm very happy to introduce the topic of hacking unmanned aerial vehicles, or UAVs, commonly referred to as drones. These technologies seem to be making their way into more and more devices that are, taking the world by storm via land, sea, and air. Drones typically implement varying levels of security, with more advanced modules being resistant to typical embedded device attacks. Today, we're going to talk with someone who has set out to use precision side channel and fault injection techniques to exploit an otherwise heavily fortified embedded device. I would like to welcome Gabriel Gonzalez-Garcia, who's the Director of Hardware Security at IOActive. He's completed hundreds of projects involving reverse engineering of embedded devices, code review, integrated hardware and software penetration testing, and many other topics. His areas of focus and technologies are hardware and embedded systems. He also has special interests in low-level attack vectors, including fault injection and side channel analysis, which we're going to dig into quite a bit today. He also typically explores novel attack pathways. He has worked in automotive, aircraft, smart grid, SATCOM, ATM, IoT, and utility industries, among others. Welcome, Gabriel. To start, I would like to ask you, how did you get into hardware hacking and messing with embedded devices in the first place?
So, it's always been an interest since I was a kid, right? So many people that I got into hacking, I think we all started very young, and I was always interested in low-level implementation on the operating systems, and especially microcontrollers, smart cards. I tried to build my own smart card reader when I was around 12 years old. So that's more or less how I started, and then over the years I began more interested in these devices with a chip that control the routers. We have them in the cars and everything, right? And that's how I grew a little bit into that area.
Wow, awesome. Yeah, I think it's a very unified story coming from a lot of folks early in that, it sounds like a lot of people that are in this area typically are messing with devices pretty early on, right? They're tearing stuff apart. They're looking at things. It sounds like your story is no different there. So for this project in particular, why exactly did you choose to focus on hacking UAVs, and how did you come to the decision to really explore this in depth? Because there are a lot of embedded devices out there. There's a lot of different areas. I know that drone hacking sounds really cool and futuristic, and I know it's very kind of timely in terms of where we are with evolving technologies in these unmanned aerial vehicles. But can you walk us through kind of how you got there and how you really began to start this project?
Yeah, I think you put it very well in the introduction, right? There are devices that they are kind of recent in the where they begin to be more available to everyone, and there are more commercial applications for drones, and there is even for hobbyists, right? They are everywhere. People grabbing videos. So that's more or less the how we got the interest, or how I got interested into this. It was always we always choose an area of research that is not very deeply explored, and so there are still things to be applied, and you need to look a little bit into the potential attack vectors. It's a little bit of novelty on the some specific attacks that come to each industry and on each application, and this is the same for UAVs. And that's how we chose the target, right? It being something that is new to the market, and we wanted to understand them a little bit better, so we can, of course, later apply to other projects, and all the things that we learn here always match to similar devices or even other types of drones.
Right. Okay. Yeah. No, certainly that That makes sense to me. It's always interesting to see what people choose to look at, especially with a longer project like this, like with security research. I think it's very calculated, what you choose to look at and the approach you go about when you're doing kind of your initial lay of the land there, right? If you're doing a pen test, it's reconnaissance or enumeration, whatever you want to call it. But actually choosing the target that you're looking at, I think, is very, very important, that part of the process. So I guess not everybody has a background. For anyone listening on what exactly your project was, could you walk through it, maybe briefly talk about, what you chose to target, maybe some of the methods that you used and kind of outcomes? What did you accomplish and what did you find?
Yeah, sure. That's a good question, right? Because I mean, as you mentioned at the beginning, we explore how to apply fall injection to drones, to this specific DJI drone. And the first thing that we always do when we try to attack one device is look at the whole attack surface and what the potential entry points, right? And the best or the most obvious one is the wireless access. Something these DJI drones have something that is called OcuSync, that is used to pair the remote controllers and transmit the video in real time with high quality. But there is also a control channel that goes on that one. There is, of course, the mobile app kind of attack surface, because since these drones also have a Wi-Fi, you can control them with the mobile app and also send commands. So that's another attack surface. And another one is the backend application that holds the firmware updates, commands, and everything, right? And there is one, but these are more or less covered, right? There is more research. There were at the time vulnerabilities published on the mobile apps and the APIs, and there was also some small research on the RF communications. But something that we wanted to explore is how these devices are, or how well protected they are against physical attacks, right? And when we think of physical attacks, of course, we need to have access to one drone. This is not something that you can do while the drone is flying, or you cannot intercept the communications. But it's a very important step when we analyze a drone or any system, because what we want to have as researchers, or well, the attackers, right, is to have access to the firmware, to the latest version of the firmware, because there is where all the remotely exploitable vulnerabilities are implemented, right? And in this particular case, if they distribute the firmware encrypted, so they do a good job on trying to hide that part. So having access to the firmware, it helps potentially uncover all the vulnerabilities. And it's also very important, or something that also companies try to protect against, because it also exposes IP, right? All the effort that they've done developing video processing algorithms, compression, and the whole control of the motors and the PID systems, the GPS and everything. If the competitor can get them, it's hours and hours or years of research that are also exposed. And later on, once you have access to one specific device, you can get crypto material that, if depending how to use, if for example a key is shared between multiple devices, that's sometimes common when you distribute encrypted firmware, because either or you encrypt the firmware with a different key for each device, or sometimes the manufacturers choose to have one key that is shared between all devices and is stored in the device while the device is in the manufacturing mode, and then is deployed. And if you get access to that secure key by some other means, like for example enabling JTAG, that we can get into that later, there is a way to get that key, and then you will be able to decrypt the firmware, or sometimes also forge a new malicious firmware update and compromise the device. So that's the attack vector, and why we chose this path, right? To understand a little bit more how well protected the devices were and how far we can get it using these techniques.
All right. Yeah. I think when people typically think about, hacking drones, in my mind and, probably in popular media as well and in movies and whatnot, you typically see somebody break out some type of RF or like radio frequency device, with a big antenna, and they, are looking at, the actual wireless communication that's happening over that protocol. But, this is kind of where I think reality kind of diverges from fiction a little bit. You mentioned that there was some research into the radio frequency protocols and the channels used for communication from, let's say, the remote to the device for control and feedback video and all that. But in this case, I think that you kind of illustrate a reality here when you're working with embedded devices where, and especially with security research, you need to know what's existing on the device already to be able to uncover what could potentially be exploited in the field. And usually that means you need to get your hands on firmware, right? Like you mentioned. And so that kind of transitions you from working on kind of a black box only project where you know nothing about what the internals of the chip look like on your board, to you're starting to get into gray and white box realm, because you can actually get access to the firmware. You could potentially obfuscate or decompile it, assuming that it's not encrypted, as you mentioned, and you can start to actually look at what's running on the central processor on the device, which will give you insight into what else you can do. And that's really driving all of the communications, all of the other chips on the board that are responsible for the operation of the device in the field. So I guess maybe could you talk to us a little bit about, for those that are listening that aren't aware, what exactly is a fault injection attack, and why is it so difficult to achieve, right? I don't think a lot of people understand the specific hardware. All of the variables here have to be, I think, very precise to be able to, one, detect if the attack worked, and then two, to even get it into a place where you can begin to systematically, let's say, perform injections on the chip that you're trying to perform the fault injection attack against. So yeah, maybe you could give us a little insight there.
Yeah, exactly. That's a very good question, right? Because there is a difference between traditional vulnerability exploitation. When we find, for example, the zero day on a firmware, it could be, for example, integer overflow, buffer overflow, even command injection, right? Or maybe a memory leak. But when you find those vulnerabilities, the vulnerabilities there is going to be easy to reproduce, right? Of course, writing the exploit can be more or less challenging, but if the vulnerability is there, it's there, and you're going to find it in that version of the firmware in every device that you find, right? When you come to fault injection, there is a different approach, because here we are not targeting the firmware or the software that is being written, although we can target specific features. But what we are doing is altering how the chip behaves in a normal way, right? It's like altering. What we are actually doing is altering the electrons that flow through the internal of the chip, that go through the transistors, and we do that by different attacks, different types of techniques. But what we do is change the currents that are inside the chips. So, for example, when the processor is reading an instruction and moving memory from one side of the bus to the internal bus, right, from the memory location to the register, to the internal register, if we kind of tamper with the current that is going through the chip, if we, as an example, we briefly cut the amount of electricity that goes into the chip, there is not going to be enough power to turn or to switch to flip bits from 1 to 0 or to 0 to 1. So what happens is that we can alter the values that are in registers. So that way we can abuse that to gain specific advantages or bypass features, right? For example, there is, as I was mentioning before, there is a common attack, or a common attack. There is we usually will use a fault injection to re-enable JTAG. And for those that don't know, JTAG is an interface that all the chips have physically. It's a physical interface that anyone can connect to and gets you full access to the chip. So you can read memory, you can write memory, you can read the register, you can debug the instructions, right? You can go instruction by instruction, debugging what is on the chip. And when devices are shipped, they should all have the JTAG closed and currently disabled, right? Because if not, it has a vulnerability. Anyone can go, plug in the debugger, and read all the crypto information that you have there with the firmware or things like that. But with there are some ways to protect JTAG. For example, the chip or the code that controls that part within the chip can look for a specific value in a register. Let's say, for simplicity, that is all ones, right? 1111111. If in one register is everything is one, then the JTAG is closed. And if everything is whatever other value, the JTAG is open, right? So that's something that similar cases are in the wild. So if we manage to time the glitch or to cut the current very briefly, that what we do is to short the VCC lines, the powers that goes into the chip. We short them very briefly by microseconds or milliseconds, depending on the chip, right? For 1 millisecond, so to speak, while the chip is reading that value, right? It's reading the value that controls the JTAG. We check it into a register, we copy it into a register, and then we do a compare function, right? That's how it works. If we manage to reduce the current when it's copying the value into a register, instead of being 111, pretty likely it's going to turn to be 000. And that is going the code is going to go, okay, it's a different than 1, so let's open JTAG, right? And that way you can bypass the security feature by manipulating the bits. It's not actually manipulating the bits. What you're doing is reducing the amount of power that a chip has, and then it will not be able to flip bits. And that's one approach, right? Modifying that, shorting the current. But it is the one that we use on the drone is we use, instead of doing voltage glitching, which is the most common one, we used EMFI, which is electromagnetic fault injection. And why we chose that? Because these drones are, even though they might seem simple, they are very complex. So the PCBs and the hardware architecture is very complex. They are very tiny in terms of PCB size. There are multiple layers, and in the size of a phone, they have like 4 very big chips, and it's very difficult to get access to the paths of the specific points of the chip that draw the current, right? That draw the voltage. It would require to do PCB surgery, and of course, drones are not something that is cheap, right? So if we risk damaging 2 or 3 drones, we are already in the tens of thousands of dollars. So that would turn out in a very expensive research. So that's why we chose electromagnetic fault injection, which in this case, it doesn't require any PCB modification. It's just a probe that you place on top of the chip. And what you do is you run a very high voltage current through a coil. And when you run that current, you induce electromagnetic field, right? This is physics. So you do electromagnetic field, and that electromagnetic field goes through the chip. And since this is an induced current, and this electromagnetic field is going to induce a current in the transistors that are inside the chip, and it's going to have a similar effect, right? You are modifying what the values of registers, the values of transistors that are around. And if you manage to time the feature that you want to target with the location and the pulse that you inject, then is when you can get a win, right? And when we use electromagnetic fault injection, there is another variable, because with voltage glitching, is just you have like the cable that gets the power to the chip, and that's it, right? You short it very briefly to ground, and that's it. But with EMFI, you have another variable, which is the specific location on top of the chip, and also the space between the chip and the probe. So usually you place it as close as you can, but it can also, if depending on the chip and how the package is, you might need to leave a little bit of space, so the glitch is not as powerful, or maybe you need to be a little bit closer. So as you can guess, there are many variables that go there, because you need to first time the glitch with the specific time with that memory is being copied from an internal memory location to a register, right? It needs to happen in that specific time, and then you need to find also the right location on the chip. So you need to go with a space of millimeters, right? You move 0.1 millimeters. You try many times. You move to the next location. You try and then you have to do whole campaigns that take hours and hours to be able to know the exact location that you can reuse to perform an attack. And after you have the location, try to target the specific feature that you want to bypass, right? So it's a very lengthy process because there are so many variables, and it's not something very deterministic. So that usually it's not something that you have the location, you inject the glitch, and then you get it, right? So it even depends. Even when you have the chip, it works perfect for one chip. It's more or less the same location. You get a different chip, the same part number, but it's a different timing, right? Because the internals of the chip, even though they might be built in the same way, they might be slightly different. So that also takes into account. So it's a lot of tries. Usually, what you have some parameter ranges. So it's not like a fixed location and a fixed timing. You have a range of, let's say, 100 milliseconds. I know that I need to glitch between 1,000 and 1,100, and then you begin doing that, and then you will eventually get the successful attack. So the whole process, the bulk of the time is to understand the parameters, to learn the location, get how strong you need to inject the glitch, the timing, right, and then reduce that. But you begin with a very wide area and all the delays that you have in the world, and then you start reducing that. And when you have that into a range that you can do in maybe 6 to 8 hours, for example, you let it run, and then you get the success. So that's more or less how it works.
Wow. Yeah. I mean, so how long did it take you on this project? I think it was a few weeks, right, to have a reproducible glitch. Okay.
Yeah. Because first you need to understand how everything works, and this because when you do the full injection attacks, the first thing that you need to know is to determine the parameters. You need to run. What we do is to run a software that we can control, right? So it's basically there is information on it online. There is a loop with counters, and that it runs, and then the prints when all the counters are completed, all the 4 loops, nested loops, it's gonna print, for example, 10,000, 10,000, 10,000, right? And then you begin injecting glitches, and you begin finding the location. And most of the time, nothing happens. Sometimes the chip reboots because the glitch it was too strong, or maybe you glitched the CPU and it got into memory fault, and the whole chip had to reboot. Sometimes, as I said, nothing happens, and eventually you will get instead the loops, instead of returning 10,000, they're gonna return 8,000 or maybe 20,000, right, or whatever. So that means that you were able in that location and with those parameters to make the chip behave differently. So either you were able to skip extraction, or there is a register that got changed the value while it was copied and between memories, and that's the first stage. And that usually takes a long time because there are many parameters. Sometimes you have the XYZ table and it move away. You come the next day and everything is ruined. the probe was in a different position. You have to redo everything. So it's a lengthy process.
Yeah.
But after that one got completed, I was able to get a successful git after a couple of days of test. Right.
Wow.
So you let it there, and then a couple of days, I was able to get a full call execution on the devices.
Amazing. Yeah. So it sounds like a lot of trial and error, essentially. I mean, and it's, to some extent, that's what any kind of hacking or manipulation of a device is trial and error. But with this, like you mentioned, all of the variables that come into play here, I mean, really, you are doing some kind of a physical manipulation of the chip, but it's not physical in terms of like resoldering components on the board and removing things. It's physical in terms of the electromagnetic frequencies that you are manipulating to actually affect the physical components of the internals of the chip itself. Yeah, and I mean for this, like I'm probably gonna butcher this reference because I don't remember all the dates, but I do believe there's a natural occurrence of this, right? I think it was back in the 90s or early 2000s. Belgium had an election, and it was one of their first elections. They used electronic devices to count the ballots, right? That were cast for the election. So they did the electronic election, but then they also kept the physical ballots and counted those separately. And I think they found a pretty significant error in the device, and they couldn't figure it out for the longest time. I think they were off by about 10,000 or so votes, which was quite a lot. And it turns out that somewhere on some physical component on the voting device, there was a bit that was flipped, and they couldn't figure out why. And it seemed to have been flipped in the volatile memory, the not the actual hard drive storage of the device, but in the actual memory while it was performing the counting operation. And I believe they attributed it to a cosmic ray or solar flare or something,
Yeah.
some kind of electromagnetic radiation from space. Essentially, they said came down and actually flipped the bit. So this is something that actual devices, physical devices on this planet, I think deal with every day. And there are
Exactly.
varying levels of protections you can do to kind of keep that from happening, right? Shielding and whatnot. But that's kind of a natural occurrence of what you are trying to simulate artificially
Exactly.
here, right? So,
Yeah, so for example, all the devices that go on planes, they go
mhm.
through similar tests because they are exposed to more radiation than on Earth, right on the ground. So
Yeah.
they have special testing equipment to simulate those scenarios as well. Yes.
Wow, it's really cool that we can take advantage of that to actually perform manipulations in any kind of controlled sense, right? Um, so let's talk about the hardware that you used a little bit more because I'm very
Mhm.
interested. I mean, sometimes I deal with sometimes I scope penetration tests, and I believe there was some guidance released through AutoISEC and a few other agencies here, at least in North America, that recommend trying to perform fault injection and side channel analysis as some kind of glitching against the hardware that go into, for instance, vehicles that are on the road. And so we get a lot of questions, I think, when people come to us and say, hey, can you perform, fault injection against our device, right? And, they kind of leave it on there as an afterthought, as something you can kind of tack on at the end. And I think a lot of people are pretty astonished by the increase in, let's say, effort that is required to do that. So I think it would help, I think, a lot of the listeners to hear kind of what goes into what you have to set up with the hardware itself and what kind of
Mhm.
specialized equipment you need to do stuff like this. You can't just, I think a lot of people have the misconception that you can just go, buy a chip shouter, for instance, online and just, tape it to a ruler or something and kind of, hang it over the device and do that for, a few hours and call it a day, right? But for this, I got a look at, I believe at the SCAR presentation that was given, there's a picture of your setup. And I mean, you had an anti-vibration table, I think, involved with it. You had a very precise X, Y axis, Z axis
Mhm.
positioning and then the actual injection piece of hardware was very large. I believe you used something from Rescure, if I remember correctly. So
Mhm.
yeah, please walk us through that and talk about kind of, how you chose that hardware and what went
Mhm.
into setting all that up.
Yeah, exactly. So for that one, we chose the Rescuers gig that well, as you know, they offer they have their own equipment for that, right? And some specific or things that you need for EMFI. As you mentioned that very well, we didn't have an anti-vibration table. That's not required for EMFI. That's more for laser injection. But for this one, what you need is an XYZ table that helps you move to certain precise, right? It need to be. I think it doesn't need to be very precise. I think any 3D printer can of go into that precision because 3D printing is also very challenging when it comes to moving just by a few millimeters or microns even. So what you need the table to be set up because that's a key part when you have to when you're going to perform the MFI attacks because otherwise you wouldn't be able to repeat the exact same location because repeatability is key here, right? If each time you are having a different position, it would have been a mess. It's impossible to find the exact location. So you need to have a setup that lets you go to the exact point of start, and then you can repeat that over and over again until you find the right parameters. So the table is one is required, and then of course the MFI probe, which is Riscure has those. As you mentioned, there is the chip shouter, right? That is from New AE. There are other vendors as well that offer that part. I think even the UI guys, they have this Pico EMP. That is a cheaper version of electromagnetic fall injection tool. Of course, it's less controllable, but you can also do some things with that. I think it all depends. It's a little bit of a trial and error, and it might work with the Pico MEP, or you might use something that is slightly more power, right? Because the thing with the Pico MEP is that I think you cannot control very well the strength of the chip. Is always the strength of the pulse is always the same. While with the others you can control that. Specifically with Riscure, you can control the strength of the pulse as well. And then the rest of the things that you notice a controlling system. There is something that interfaces with the drone in this case, because you need to be able to assess whether the glitch make the chip behave differently, or if it was into reset mode, or just set timeout and then you need to reset everything. But that one is I think that's custom and needs to be programmed for every system, right? So those will be the main setups. You have the EMFI probe, the table, which for EMFI is very, very required, and the control system.
Wow. Yeah, no, definitely. I think that for this in particular, actually going through the process of performing glitching on a chip, first off, sounds like, there's definitely some things that you pick up. I think with any skill, there's something that you say, oh, I learned such and such X, Y, and Z last time, and I can quickly, try to adjust these variables more the next time. But yeah, with this, it's so interesting because of that variance in, as you were mentioning, the actual physical properties of each chip, even if it's the same chip, the same part on the same board, right? Or same type of board rather. So yeah, I mean, I think that's very. I think it provides a lot of clarity to people listening to see, what is required to actually carry something like this out. So I guess I have a question for you now about after you found this glitch. It's reproducible. You see that it's feasible on this chip, right, on this device. How can you pivot now as a security researcher, or if you're thinking about as an attacker? How can you extrapolate this kind of technique and leverage a common exploit across devices? Do you think that that's something that's feasible with what you found, or is it just getting access to understanding the internals of the chip at that level that this allowed you to do, right?
Yeah, so that's a good question, right? So in the specific of this drone, the DJI drone had a lead core chip, the one that we are targeting, which is there is no information around, right? But you need to buy it, and then when you buy in large quantities, that's when they give you all the information. So that's all the data sheets and everything is not public. So these attacks will be specific to this chip. So after I was able to find the glitch, or let's say the vulnerability, right, that you can kind of exploit, the next step was to identify a way to abuse this weakness of the chip. And as I mentioned, there are different ways that you can do it. One is targeting the JTAG, but as well, this debugging interface, there is no public information. We are required to desolder and remove all the chips and look for all the balls on the BGA and the BGA, which is what the chips that don't have like outside pins. They make connection with the board on the bottom part, and there are hundreds of balls. So you will need to potentially test 20 or 30 balls and see if you can manage to get the JTAG interface. So that's a very lengthy process, and you can also destroy some drones in the way, which is not ideal. So I targeted the firmware update feature, right? So now that I knew the position and the parameters that were more or less localized, what I did was to begin injecting glitches while I was transferring data to the drone, right? So basically, what the firmware update part, what it does is gets firmware from a USB and then begins the update. And for that, what it does is copy a large amount of data because the updates are worth a couple of gigabytes. So it copies lots of data between one memory location to another, basically between the USB part to other memory. And for that, what it executes many times a memcopy function, right? There's basically what you do is load into a register from memory, and then you copy that memory to another address, right? To another address in the space. And what we did was to begin injecting glitches while this was being performed. And what I was able to achieve was to get an instruction modified in a way that I could control the address where the memory, the data that I was supplying was located, was provided, right? So basically, the exploit looks like the firmware, right? I need to provide a firmware, a modified firmware myself, because it wouldn't be possible to be signed by the company because something that is malicious. And while I provide this firmware that has the address of the target address that I want to overwrite and the data that I want to put on that address, that would be how I need to create that firmware. And then when I was supplying this custom firmware, I had to inject all I need to begin the campaign, begin injecting glitches, and eventually the instruction would flip to the one that I needed, and it would copy my firmware into the memory location, right? I would overwrite memory addresses that I wanted. So that's how the attack was actually performed. And to the question of how this would apply to a different device, as we were talking before, this is very specific to the chip. So this could apply the same setup and everything. We need to have the same chip. There's a lead core chip, and it was running an Android device. So we should have a similar set of environment, so that it could be more. You don't need to go and research the whole space of parameters. But if, for example, the next version of the chip uses a completely different, the next version of the drone uses a completely different chip, everything will need to start from scratch, right? So everything, all these fault injection attacks are tailored to the chip itself, because it's a vulnerability more on the chip rather than on the software that is executing. Although we target software features that we want to bypass, but the problem is in the chip as well. So that's more or less how
I see.
how it is.
Yeah, so essentially you're able to reflash the firmware onto the chip and circumvent whatever secure boot processes they had or secure flashing processes that the vendor had. Yeah, and this might not be directly, it's not something that you immediately have access to do this on every drone. Like you're not able to,
Yeah, exactly.
There isn't some secret mechanism you've discovered here. It's basically just modifying it so it will take it in that instance. That makes sense. Okay.
Yeah, it's more about also because this is a complex, because there are lots of literature on fault injection, and there is a lot of that on microcontrollers. There is less available on complex chips or complex SOCs. On this one specifically, this chip had 4 cores, and that makes it even more difficult, right? Because you need to place. If the code you're targeting runs on a core, is jumping from core to core, it makes it more difficult to find the location. And so, well, there are things that we try to reduce those variables. Also, all the learning experiences and that we were able to use these wild jumps, or there are different ways of use how this attack is performed. These are also learning experience that you can then reuse in different projects, right? So maybe the whole setup is different, but at the end of the day, also the attack that that is achievable. You can use it in a different chip, right? Even you will need to narrow down all the parameters and get that set up. And when that is done, then you can use this technique of manipulating, for example, the firmware update mechanism.
Wow. Yeah, no, that's amazing to see something like this in action, and it's something that you hear about again. But I think it's very rare to have someone who can kind of sit down and explain, the process and also, realistic outcomes, right? I guess I do want to wrap up soon, but I do want to ask, how did the vendor react to this disclosure? If you can, talk about that a little bit. What steps did they take after? And kind of, that's always interesting to me when you do some kind of responsible disclosure like this. How was it working with DJI with this project?
Yeah, it was the DJI team was very good. They handled that very well, right? We contacted them. We found the security contact. I can't remember exactly how we got to that, but we shared the report and everything before we published anything, of course, and they reacted very promptly. So we set out a call. I was discussing with them what I found, and they even granted me with a bug bounty for the finding, and then they said that the problem with these things is that in the current drones, you cannot do much. Well, there are software mitigations that you can do to mitigate, but if there are no glitch detectors implemented in the chip, you cannot change the chip while something is right. Already so, right? So I knew that they were beginning to investigate into the full injection and I evaluated for the upcoming projects. So I think they behaved very well. Everything was very, very fast. They didn't delay anything. So I was very happy with their security team.
Wow, that's great. That's great to hear. Yeah, I mean, mitigations on this are difficult, right? The hardware is the hardware, and changing that can be costly, and also, kind of like a almost like future recommendations for future platforms that they create. Maybe they could take that into account. But yeah, as you described it, that seems very difficult to protect against, essentially. Well, yeah. Amazing. Thank you, Gabriel, for joining me today. I really appreciate it. I really enjoyed talking with you about this and getting in depth into the process of actually performing fault injection. Talking about this. I know that we talked about this with regards to UAVs and drones, but I think that this is applicable really to any embedded device, right? And anything that uses a chip that is, I would say, somewhat simple. I think as the system gets more complex, it's more difficult to actually do something like this, right? But I think this was an amazing discussion to kind of jump into that. Do you have any final closing thoughts for those listening?
Well, just to mention that the full injection attacks are something that is real, right? It's being exploited on the wild, and the conferences, security conferences out there. There is always new kind of attacks or different devices that have been bypassed by full injection. So I think it's something that needs to be taken into account. Of course, depending on the business scenarios, each company has their own risks, but it's something that it's not futuristic. It's something that is already here, right. And it needs to be taken into consideration.
100%. Yeah. No, it's very real. All right. Awesome. Thank you so much. Well, thank you everyone listening for tuning into this episode of Empowering Tomorrow's Automotive Software Podcast. We hope that you as the listener found our discussion insightful and valuable. If you enjoyed today's episode, don't forget to subscribe on Spotify, Apple Music, or wherever you get your podcasts. Feel free to share this episode with your network and leave us with a review. We would love to hear your feedback. This concludes our episode. Please check in again for a new one.
Thank you for joining this episode of the Empowering Tomorrow's Automotive Software Podcast. Please leave a comment or review with your feedback or what you'd like to hear in future episodes. To learn more about automotive embedded systems and ETAS's capabilities, visit our website at ETAS. That's ETAS.com.